So today we have kind of a change of gears. What I want to talk about today is kind of the beginnings of image compression. Okay. So this lecture and the next one are going to be a little bit different in the sense that, up to this point we've kind of been talking about things that were more related to image understanding, image processing, like things where you visually look at an image and you do something to it. You find the lines, you find the edges. So today we're going to actually be almost totally agnostic about what this data is. Could be an image, could be a text file, but the principles are the same, right? And so, as you know from browsing the web, there are lots of different kinds of image file formats, right? There's, when I was, in college, as I recall, the main file format was bitmap, which was like the Windows 3.1, crappy. I don't think it was even a full, I guess I don't remember the bit depth, but basically they were low quality images and they took up a ton of space, right? These days, you browse the web and you see file formats like PNG, GIF, JPEG, TIFF, right? And so what I want to talk about this lecture and the next lecture is what is the mathematical basis for these formats and how they work, right? And so the topic of today, so there are basically two kinds of image compression, right? There's either lossless or lossy, okay? So lossless means that the uncompressed image is exactly what you asked the coder to create, right? There's no loss or no corruption of information, right? And so from a perspective of image processing, lossless formats are important. So lossless compression is important for, so from a kind of, I don't want to say this is the way that the real world actually works, but from a, kind of perspective of things like, medical diagnosis, you don't want to acquire this medical image and then, possibly corrupt it with artifacts that you may get from a lossy compression algorithm like JPEG, right? So you want to make sure that everything that you get in that image is something that you actually acquired with your sensor, right? For legal reasons, although I don't want to speak for the legal profession, but you may want to say, okay, I need to preserve evidence, right? I need to archive this document, and I can't have any sort of differences from the original document with what I've archived, right? And for things like satellite imagery, places where you basically have gone to a huge amount of trouble to acquire this image, right? It's super expensive to get a satellite image, so you don't want to throw away any of the information that you acquired, right? So in general, archival things, or just general high quality imaging, right? So one way I think about this is that if you could do, if you could take your original image file and compress it down to some very small size without losing anything, well, why wouldn't you do that, right? These days, it's getting cheaper and cheaper to transmit information, so it's not like we are in this sort of resource-constrained situation where we have to throw away information even in order to be able to transmit the image back and forth, right? So these days, it's not like that's the kind of issue that it was. And in general, the biggest reason that we want to do lossless compression is not really related to image processing, but it's related to just general file compression, right? So, I would say the most important one is kind of general file compression, right? So if I take a folder on my desktop and I zip it up, right, I can't afford to lose anything in that folder, right? Like, it's not like I can afford to take my, project proposal and lose some of the characters or some of the images in it or corrupt those characters into other characters, right? I can't disturb what I got, right? So there are, most of the time, the reason we care about lossless compression is that we want to take some original data, scrunch it down into the smallest possible size, ship that data somewhere or store it somewhere, and then be sure that when we undo it, we've gotten exactly what we put in, okay? And so to measure how well we did, we have what's called the compression ratio. So to measure performance, we can use the compression ratio . which is basically like the number of bits before we did anything, the uncompressed data, over the number of bits after. Right? So in theory, the number of bits after should be a lot smaller, and so this number should be greater than 1. Right? And it turns out that for real images, we can usually get a compression ratio of between like 2 and 10. So we can really do pretty well. So for real images, we can get lossless compression ratios in the range of, like, say, 2 to 10. Okay. And so this is why, for example, if you take the same image, so the bitmap format, like BMP, was one of the very first image file formats, and that file format basically didn't have any compression. It just was a literal list of RGB values every pixel, right? And if you compare that to the size of, for example, a GIF file for the same image, the GIF is is much, much smaller, right? That's because we're applying compression to it. Okay, so GIF is one of those file formats that does lossless compression. Okay, and what we're going to talk about next time is lossy compression. The main example of which is JPEG. So lossy compression means that I'm willing to tolerate some difference between my compressed image and my original image, as long as the compression ratio is a lot better, right? So I mean, that kind of comes back to some of the stuff we talked about in the very first week of class about what your human visual system is willing to tolerate, right? So there are many little subtle differences that you would never pick up that there was a difference between the original image and the compressed image, but the compressed image turns out to be much easier or much more compact, right? So that's what we're going to talk about next time. Okay, so in order to talk about lossless compression, we need to get into some slightly new mathematical concepts, okay? And these are concepts from, for example, what's called information theory. So we need to first talk about the kind of image histogram, okay? So it turns out that the way that we can compress an image depends a lot on its histogram. So recall the image histogram, and we're going to think about this as a probability mass function. Right? So this lecture actually has some ties back to probability. So basically, I'm going to call Pi the probability that an image pixel has intensity I, okay? And that's just basically, the number of pixels where this is true over the total number of pixels, okay? And so I can talk about how many bits it takes me to represent this image on the average by saying the average bits per pixel is equal to the sum over all my levels of the probability of that level times the number of bits I use to store that, which is basically like the expected value of the number of bits, right? So in image processing, we often talk about a gray level image that ranges between 0 and 256, or 255, sorry. So that means that in theory we have an 8-bit image, and if I don't do anything fancy, that's like saying, well, so for kind of uniform coding, this BI is equal to, the same number, for example, 8 bits. And so that means that the average bits per pixel is 8 because I'm using 8 bits to describe every pixel, right? The question is, can we do any better than that, right? And the answer is yes, obviously. And the reason for that is that the pixels that occur more frequently, right, we should be able to code those with fewer bits. And the pixels that don't occur so often, the levels that don't occur so often, we should be able to code with a large number of bits. under the assumption that we don't have to use those code words very often, right? So that's actually similar to how Morse code works, for those of you that know Morse code, right? So the idea is to use fewer bits to describe more frequent symbols. Right? And so an example of that is Morse code, right? Where if I want to send an E, that's just a single dot. But if I want to send a Q, that's like dash, dash, dot, dash, dot, right? So the point is that if I'm a telegraph operator, I don't want to keep on sending, you know, a 3 or 4 symbol thing for every E that I send. I just want to send that one dot because E occurs so often, right? And that's the philosophy here. And so the question is, how do we design the optimal code words that correspond to every pixel? So instead of E's and Q's, we're talking about gray levels in an image, right? And we want to figure out how should we take the 8 pixels, the 8 bits that we used to use, and maybe change that to different numbers of bits per code word, okay? And so the main thing I want to talk about first is Huffman coding. So let me just see, show of hands, who has seen Huffman coding before? Only a couple. Okay, I wasn't sure whether you did Huffman coding in some other class. Okay. Algorithms. Okay. So maybe if you're not a, you know, CSE major, you haven't seen. Anyway, so we're going to do Huffman coding. So here's the idea. So let me do a try to decide whether I want to do this. Yeah, let me do this way. So let's suppose that we have an image that only has 8 levels. Okay, obviously, real-world images have a lot more than 8 levels, but this is going to be my toy example. Okay, and so what I'm going to do is I'm going to make a table of the level, which is really I, and the probability of that level, and then I'm going to have a uniform code. Okay, so let's suppose I have the levels are 1 through 7, or 0 through 7, and I'm going to assign them some probabilities, okay? So this is just like the frequency of how often this level occurred in the image that I have. So I can see that these levels at the top, you know, are more frequent. These levels at the bottom are less frequent. But if I didn't know any better, I would just use a 3-bit code for each level, right? So I just use my normal kind of binary code. Okay. And so obviously the length of each of these code words is 3. The average number of bits per pixel for that would be 3. Okay. So now let's suppose we think about a variable length code. Okay, so instead, I could use my idea of saying, okay, these guys, I should be using shorter code words. These guys, I should be using longer code words. So here's a proposal for a variable length code. So here I'm only going to use 2 bits for each of these guys. I'll use 3 bits for this guy, 4 bits here, 5 bits here, 6 bits here, and 6 bits here. Okay, and so the question is, do I do any better, right? And so what I would do is I would say, okay, I'm going to multiply 2 times 0.19. That's, so if I want to compute the expected value of the code, what I would do is I would say, okay, I'm going to take, you know, 2 times this, 2 times this, 2 times this, 3 times that, and so on, add those up. So here, if I were to do the computation, obviously here, my average length would be 3. If I do the computation here, my average length would turn out to be 2.7, okay? So I've compressed by 10% the number of bits that I need to send this message, right? And so this is a compression ratio, right? So the compression ratio would be 3 over 2.7 is approximately 1.1, right? So I've got basically 11%, better compression than I would if I hadn't done it, right? And so what I want to talk about is, okay, so I gave you this proposal for this code. How could I know, number one, what's the best code, and number two, what are the fundamental limits on how well I could code, right? Is it possible that I could get this down to 1 bit per, code word, or, 2 bits? I mean, how do I know how close 2.7 is to the theoretical minimum that I could possibly achieve, right? And the answer to that question has to do with a concept called entropy, okay? So, what's the best we can do? So this is related to the entropy, okay? The entropy of the distribution. And that's defined, we call it H, as the following. Okay. So the idea is that we're going to take the expected value of this log 2 of the probability. Okay. So again, since all the probabilities are less than 1, that means the log of those numbers is going to be negative, which means that to make this a positive number, I need to flip the sign. Okay. And since we're talking about bits, I have a log 2 here instead of a log 10 or a log base e, like a natural log. Okay. And so the entropy measures basically kind of how uncertain the I'm going to put this in quotes because it's like kind of how uncertain a random variable is. Right? So for example, the kind of worst case scenario is a uniform random variable, right? The level is equally likely to be in any of the bins, right? So that's really the worst case. I don't know where that could be. Every bin is equally likely. The best case is like a delta function, right? Where I've got a PMF where it's 100% likely to be in one bin. That means I know exactly where the variable is going to be. That should have the lowest entropy, right? So basically, the entropy ranges between uniform, so the worst case is a uniform PMF, right? That means that if I were to plot the probabilities, I wouldn't know where it is. The best case is basically a delta function, meaning all the probability is in one bin and there's nothing in any other bin, right? And so we can compute kind of what these values are. So for a uniform PMF, right, that means, let me recompute this here. So for uniform distribution, that means that the probability of being in each of these things is 1 over n, where I have n levels. And that means my h is going to be, writing this again, log 2 of pi. So that means that I'm going to have basically n times negative 1 over n log 2 of 1 over n. Right? So these guys are going to cancel out, and what I'm going to get is basically log 2 of n. Right? So this is kind of like saying if I had 8 levels, right, then the entropy is going to be 3, right? Log 2 of 8 is 3. So in some sense, that's kind of the worst case. The delta function. So let's suppose that I have all the probability mass in one place, and then all these other guys are equal to 0. Then my h is going to be minus 1 times log 2 of 1, which is 0, right? and then I'm going to have 0 times a whole bunch of other stuff. So the entropy is 0. So basically, kind of what I'm going to get at is that, you know, when everything is entirely predictable, the entropy is 0. When everything is maximally unpredictable, the entropy is, you know, kind of like the number of bits that I would use naively to just code that uniform distribution. Okay? And so it turns out that the entropy, and I'm going to put this on another slide here. So the entropy is the lowest number of average bits per symbol that can be used to code the distribution. Okay? And so that gives us our lower bound for what's the best that we could possibly do, right? And so what this is telling us is that for a uniform distribution, where each of the levels is equally likely, the best I can do is the standard code, right? So in my case over here, if each of these levels was, you know, 1/8, then the 3 bits would be, by the rule of entropy, the best that I could do, right? But since this is not uniformly distributed, I have some best case, right? I have some, you know, best case possibilities between 0 and 3. And so the question is, what would be the entropy for this distribution? Well, I can figure it out, right? So let me go over to MATLAB and say, okay, if I have my vector of probabilities, which I'm going to put in as what I said before. Oops. Okay, make sure that these sum to 1. Okay, so then basically my entropy is going to be p dot times log 2 of p, and I'm going to sum that up, and I'm going to make it negative. So turns out for this distribution, the best I could possibly do is 2.65 bits per pixel. And if I go back to my, you know, sheet, I found out that I got actually 2.7 bits per pixel. So actually, this is pretty close to the best that I could do, right? I can't get that much better than this, okay? So let me pause and ask for a second. So comments or questions about entropy? Okay, so that's kind of half of the answer to the question I was asking before is, how do we know what's the best thing that we could do, right? So the next question is how to design a code that approaches this value. Okay, and so the key concept is called Huffman coding, or at least one of the key concepts. So Huffman coding is basically the optimal, that is to say, the minimum average length code for independently coding n symbols. Okay. And so here's how it works. Okay, it's a really easy and fun algorithm to apply. So let me write it down. So first we arrange the symbols in decreasing order of probability. And we think of these as nodes or leaves of a tree. Okay. Then we merge at each step the two nodes with the lowest probability. We assign 0 and 1 to the top and the bottom branch, which will become clear once I do an example. Then I iterate this process until I'm done, and then I read the code from root to leaf. Okay, so what does all this mean? Let's do this example with this guy here. Okay, so let's take this example. This guy is basically almost already ordered, except my level 1 is actually the biggest level. So what I would do is I would say, okay, I'm going to make a list of these symbols from highest probability to lowest probability. And each step, I'm going to look at my current list, and I'm going to merge the two nodes that have the lowest probabilities, which at this point are these guys. Okay, so I'm going to merge them. That's going to make a new node, which is the sum of these probabilities. And I'm going to assign, you know, a 1 to the top branch and the 0 to the bottom branch. Okay, and I just keep on doing this. And I say, okay, now I look at what I've got left, and now these guys are the lowest. They merge to form this guy. Again, this guy is going to merge like this to be 0.19. This guy is going to merge again. If there's a tie, it doesn't matter. You can go either way. So like here, there's a 0.19 here and a 0.19 here. Doesn't really make a difference. So these guys add up to be 0.35. Now I have to stop and say, okay, well now these two nodes are now the smallest. So I'm going to get a node that is 0.40. Now these two nodes are the smallest. I'm going to get 0.6. And then finally, these two guys add up to be 1. Okay. So at the end of this process, I've added up all the probabilities, and I should get 1 at the end. If you don't get 1 at the end, you've done something wrong. Okay. So then I read the code back by starting at this end and going this way, right? So this would tell me that the code word for this guy should be 1, 1, right? 1 here, and then I'm back here. The code word for this guy should be 0, 1. The code word for this guy should be 0, 0. Then I have 1, 0, 1. 1, 0, 1, 0, 0, 1. 1, 0, 0, 0, 1. 1, 0, 0, 0, 0, 1. And then 1, 0, 0, 0, 0, 0. Okay. And that's exactly the code that I put together here, right? I just knew what I was going to get. Okay? And so it's pretty simple, right? I mean, you can kind of whip this together, you know, just by hand pretty fast. So I pause and ask, any questions about the mechanics of how I do this? Okay, it's pretty easy. So, like I said, I'm not going to prove it to you, but basically the Huffman code is the best that I can do. If I'm going to only assign an independent symbol to each of these levels when they come up, the Huffman code is the closest that I can get to the entropy, which is kind of like the theoretical best case scenario. Okay. And so it's nice that the way of doing this is so straightforward, right? And an added bonus is that the Huffman code is what's called a prefix code. So what that means is that no code word is a prefix of any other code word. What I mean by that is as follows. So let's consider two possible codes, code A and code B. Okay, so code A, suppose I have just 4 symbols in each case, and here is the choice for code A, and here's a choice for code B. And so the idea here is that this is not a prefix code, and this is a prefix code, meaning that, none of these code words begins any other code word. Whereas here, code word 3 begins with the same symbols as code word 4. Okay? And so why is this important? It's important because, let's suppose that we were going to code this set of symbols, right? So code A would give me 1 0 0 0 1 1 1 1 0 1 1 0 0 1 0. Code B would give me 0 1 0 1 1 0 1 1 1 1 1 0 1 0 0. Right? So the issue is that when I send this code into my file or across my channel, there are no separations between the code words, right? They just all are smushed together, right? And so in code A, so how do I do decoding, right? So in decoding, let's look at code B first. What I would do is I would say, okay, I start to follow along and I draw my divisions once I've seen a code word, right? So I'd say, okay, 0. Well, there's no other code word that begins with 0, so I know that I can make this dividing line here. Okay, now I see 1. Well, there are a bunch of code words that start with 1. I have to wait and see what happens next. 1 0. Now I say, okay, well, there are no more code words that start with 1 0, so I can draw this boundary. 1, I have to wait. 1, I have to wait again. 1 1 0, I can draw the line, right? How does that differ from code A? Well, code A is like saying 1, well, there are a bunch of code words that start with 1. 1 0, I can now draw this line. 0, well, in theory, I know there's nothing else that begins with 0, but I have to wait to see the second 0. Here, the problem is I could say 1, 1, okay, 1. I still don't know, whether or not I have, 2 sets of 3. I don't know whether this is 3, 3, or whether it's 3, 4. I can't really make that decision until I get all the way to here, right? So basically, let's just think of this sequence, right? So if I have 1, 1, 1, 1, 0, if my pointer is here, I can't draw, the line for, how do I want to say this? Basically, I can't draw the line here until I see this 0, and then I have to go back and draw this line. So the idea is, can I decode this stream of symbols simultaneously? That is, as soon as I see a symbol, can I make a decision, or do I have to wait to look into the future to see what symbol it is, right? So that's the idea, is that a prefix code can be decoded what's called instantaneously, okay? So, so let me just say prefix codes can be decoded instantaneously. Okay, and it's important, that also the decoding process has to be totally unambiguous, right? So it turns out that both of these codes are uniquely decodable, right? So there's this other concept that, if I give you some stream of symbols, there can only be one way to decode it. If there's not, then that's a really bad idea, right? So suppose, for example, that my code words were 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, right? And then I just show you a whole stream of zeros. I have no way of knowing where I could divide those lines, right? There has to be a way to uniquely decode what I've sent out, right? So it turns out that both this code and this code are uniquely decodable, meaning that if I show you a stream of symbols, there's only one way to decode it. But for this one, I have to wait for at least an extra symbol to be able to answer the question. And it turns out that there are uniquely decodable codes for which I could have to wait an arbitrary time to decode, right? I may have to wait almost to the end of the message to be able to understand what the only way of dividing those lines up is, right? So that's why Huffman codes are nice, is that there's never any of that kind of fooling around, right? I can always draw my dividing lines from the symbols as soon as they come in. I don't have to wait till the end of the message to understand how to split up the code, okay? And of course, this is definitely valuable for kind of real-time streaming of coded information, right? You don't want to have to wait until you receive the whole message before you begin to decode it. Right? So in time-critical applications, these kinds of instantaneous codes are definitely preferred. Okay, so comments or questions about this idea? So there are some variations on the theme. Okay, so basically, here what we're doing is we're coding every level independently, right? And it turns out that you can do better if you code, for example, chunks of the message. So for example, what I could do is, I can generally do better by considering pairs of symbols. Or more. Right, what I mean by that is that, suppose I've just got a binary message, 2 levels, right? The best I could do would be this, I can't actually do any better with 2 levels than sending 1 bit per level, right? That's all I can do, right? Instead, what I could do is I could say, okay, so if I've got a long message like this, what I could do instead is I could say, okay, well, instead of sending every symbol independently, what I'm going to do is I'm going to look at pairs of symbols, right? And then I'm going to use, for example, a Huffman code to look at these 4 probabilities. And then I'm going to design a code that maybe has better than 2 bits for every pair of symbols on the average. And I could extend that idea to, instead looking at, triples and have 8 symbols, right? The problem with this is that, if I was doing this for images, for example, that would be like saying, okay, if I'm looking at 8-bit images, I could say look at, every pair of adjacent pixels. So instead of being 8 bits, I would have a 16-bit code that I have to do for every pair of symbols. And so the more symbols I combine together into, one, mega symbol, the larger my table of probabilities becomes, and the more work I may have to do to actually generate the code in the first place, right? So this kind of has diminishing returns, right? I wouldn't want to do this for huge numbers of pixels, but certainly for some cases you can do a lot better by kind of chunking the message into, groups of symbols instead of just the original single symbols, okay? So that's one variation. Another variation is what I would call truncated Huffman coding. So one problem with existing Huffman coding is that the lengths of the codes for symbols that don't occur very often can get very long, right? And so you can kind of see the pattern here, right? So if this was a 256 symbol table, it could be that I have some crazy number of long code words at the very bottom of my table. And there are kind of practical reasons, for example, if I'm storing these codes in an array somewhere, but I don't want the code words to get out of control at the very end, right? So I may want to limit the length of my code words while still having good performance. And so what I could do is, to avoid, extremely long code words, for, infrequent symbols, what I could do is basically, Huffman code the most probable k symbols in the source, and then replace the rest with a prefix plus a fixed length code. In that way, things really can't get out of control too much. And so let me show you an example of that. So let's suppose that here I look at my code and I say, boy, these code words are starting to get a little bit too long, especially towards the second half. So why don't I instead say, okay, I'm going to really care about these code words, and I'm going to group the rest of these guys into a uniform code. So what I could do is I could say, I'm going to take my top list, right? So before I had, 0.25, 0.21, 0.19, 0.16. Okay, those were the values of my first 4 most probable code words, and then I'm going to just lump all these guys together into a box that says the rest. Okay, and so what do I got here? I've got this plus this is 0.14, 0.17, 0.19. So there's 0.19 of probability in this kind of tail end of the distribution. And so then I'm going to have a 0.19, which I'm going to call the rest. Okay, and now I can Huffman code this, this set of numbers, right? So I could say, okay, I'm going to, I guess I should technically reorder these guys to be in the right order. So I'm going to say these guys, I'm going to put my little box around here as the rest to remind myself that's not an actual code word. And then I'm going to do my Huffman code. This. Okay, so that would tell me that I give this guy code word 1.1, I give this guy code word 0.1, I have this guy here get 0.0, then I have 1.0.1 and 1.0.0. So if I were to go back on this, I would say, okay, here are my original code words, and I will just write down my code for those guys. And then here are my code words that I called the rest. And each of these guys is going to get a prefix of 0.0. And then I'm going to assign just a fixed length code for these remainder guys. So I'm going to say, okay, here I'm going to use 2 bits to describe each of you, right? And so here, what I've got is kind of a way to inherently limit the length of the code. Yeah?
Could we then Huffman code that?
Could you Huffman code
The remaining and use the prefix?
Oh, I see what you're saying. Could you Huffman code the remainder and use the prefix? Yeah, I guess you could. Yeah, there are lots of ways you could do that. Right. Question?
Does it matter which point I drew the box around?
No, it doesn't matter which. Well, I guess in this case it might have mattered in the sense that if I had drawn the box around the other 0.19, then my prefix for that code would have been 1.0.1 instead of 0.0, and that would have been worse, right? So this is one of the cases where the tiebreaker could make a difference because of it's not exactly a Huffman code, it's something else, right? Good question. Other questions? Yeah.
How do you know which one gets the 0 and
You mean in terms of the branches?
Yeah.
It's arbitrary. So as long as you're consistent when you make your tree, it doesn't matter. So I mean, I could flip these to be 0 on top and 1 on the bottom, and it would still be a valid Huffman code. Yeah. So don't worry about that. So if I compute, before I compute the average length of this code, I would find out that this gives me 2.75 bits per pixel. So if you recall before, for the true Huffman code, I got 2.7 bits per pixel, and for the entropy, I got 2.65. And so this is a little bit worse than the Huffman code, but I am maybe better in terms of if I was restricted to only be able to use up to 4 or 5 symbols per code word, then I could do, pretty well. Not as good as the Huffman code, not as good as the entropy, but at least I would have shorter code words, right? Okay. Other questions or comments? All right. So there are other variations to Huffman coding, right? But in practice, the code that actually gets used in the best algorithms, like for example, the code that's inside your zip files and inside your PNG files online, is an even more complicated code that's based on what's called Lempel-Ziv coding. And so let me just give you an introduction to that. And this, kind of rapidly becomes something that's hard to do on paper. So I can't do very exciting examples, but Lempel-Ziv coding which is the basis for GIF, TIFF, kind of PNG and zip files, right? So I mean, actually, I think that if you even look at one of your zip programs, there's like a LZW like extension that could be a Lempel-Ziv thing, right? There was some issue, as I recall, where this coding algorithm was patented, and so it used to be that the GIF standard, like the question was whether the GIF standard infringed on the patent for Lempel-Ziv, and so that's why they invented the PNG standard, was to have a kind of a open source way of doing the coding that didn't infringe on any patents, but basically the same kind of idea. And also PDF files apparently use Lempel-Ziv. So conceptually, the algorithm is simple. So the idea is to parse the source string sequentially into what you call phrases, which are basically strings that haven't appeared before. And then I code each phrase by giving the location of the prefix, which will become clear in just a second, which I use a fixed length code for. Plus the last bit. This will only make sense once I actually do an example. Okay, so what I'm going to do is I'm going to just make a long string of binary symbols and show you how this Lempel-Ziv coding works. And as you can see, the coding is going to be very easy to do. Okay, so let's just suppose I make up an arbitrary input string, okay? So I'm just making it up on the fly. Okay. So what I'm going to do is I am going to start to draw divisions through this string, and I'm drawing a line when I have a word that I've never seen before, okay? So currently, I start with an empty list of phrases. I haven't seen anything before, right? So I start with this 1. I say, oh, 1, that's new. I've never seen 1 before. So now I draw a line here. Then I say, okay, now I go to my Lexis symbol, 1. Well, I've seen 1 before. 1, 0, that's news to me, right? So I draw this line. Then I see 0. Well, I've never seen 0 by itself before, so I draw this line. So 0 is in my list, 0, 1 is not in my list. 1, 0, I've seen. 1, 0, 1 is new. 1, I've seen. 1, 1, I haven't seen. 0, I've seen. 0, 0, I haven't seen. 0, 1, I've seen. 0, 1, 0, I haven't seen. 0, 1, 0, I just saw, so 0, 1, 0, 0 is new. And I keep on going like this. 1, 0, I don't think I have a 1, 0, 0. 1, 0, 1, I have, so 1, 0, 0. 0, 1, 1, I don't have. 1, 0, 0 I have, so like this. 1, 0, 1, 0 I have, and so on, right? So that's basically how I divide up my long string into phrases, okay? And then what I'm going to do is I'm going to assign each of these phrases to be a fixed length code, okay? And so So how many, I guess I have, between 8 and 16 symbols so far. So what I'm going to do is I'm going to, suppose that I assigned each of these phrases to be a 4-bit uniform code. That's what I would need to uniquely describe each of these things. So this would be like, this location would be like 0001. This one would be like 0010. This would be like 0011. And I'm kind of saving my null string to be 0000. And so the code actually works by saying, okay, I code up this string by telling you what was the prefix of this string and what is the new bit, right? So for example, here I would say, okay, the prefix of this is the empty string, and the new bit that I added to it is 1, okay? So it's kind of like a pointer to the thing that I need from before, plus the new bit that made it a new phrase, right? Here, this is like saying, okay, so this prefix was 1, which I saw over at this location, and the new bit was 0. Here, well, this is something that is basically the empty string with a 0 added to it. Here, this is like the symbol that occurred at location 0011, and the new bit is 1. This guy is the thing that occurred at this location, and the new bit is also 1, and so on, right? So basically, this is the location of the prefix, and this is the new bit that makes it a new phrase, okay? So it is certainly not obvious that this actually is a great compression algorithm, right? But it turns out that this is actually like super good at squeezing down information. And one of the reasons is that when I have really, really long strings, right? So if I think about it, like if I think about the number of bits that are in an image, right? So every pixel has 24, has 8 bits of each color channel and 3 color channels. So each pixel is 24 bits of information, and in a megapixel image, I've got like billions of those, right? So for an image, this string is like extremely long, and it turns out that as I, go further down the string, that these prefixes are pretty short compared to how far I am into the string, right? So basically, it turns out that for a short code like this, it seems like I'm using more bits. I'm using here 5 bits to describe this 1 and 5 bits to describe this 1, 0. It takes a long, long string before you start to see this actually pay off. But when it does, it pays off in a big way. And like I said, that's really the foundation of zip files, right? Is basically a variation of this algorithm. The nice thing about it is, number one, as you can see, it's very easy to split up the string into these symbols. The coding part is very easy, and the decoding part is also very easy in terms of just this lookup table for how do I put this set of symbols back together. Unlike the Huffman code, I don't actually have to know the probability distribution of any of these symbols, right? There's no PDFs in this example, right? All I'm getting is this string of information, this stream of information, and the Lempel-Ziv code is learning about the frequency with which things occur, right? And so the nice thing is that there's no, knowledge of the PMF for symbols. Unlike the Huffman code, this code is exploiting how symbols occur together, right? So kind of by construction, this code is using adjacent bits to make its compression instead of just using every bit independently, right? And like I said, really pays off for very long strings, right? And in some sense, the proof of that is in how small your zip files can get, right? So I mean, like you take a big directory full of, so for example, like this would be good for anything where there is a lot of redundancy in the file, right? Like text files, right, have lots of redundancy in the sense, or lots of structure in the sense that, there are some symbols that never occur very often, like the Z's and the Q's. There are some combinations of symbols that never occur together, like ZQ, right, where there are symbol pairs like TH that occur very often. So the idea is that, this kind of algorithm is going to pick up on the things that happen a lot and not spend any time on things that don't happen very much, right? So this is, about as much as I can explain it, right? I mean, in some sense, the proof is in the pudding. If you were to write this up yourself and apply it to an image file, in theory, I could have assigned this as a homework, right? Because it's not actually that hard to write the coder and write the decoder, and you would find that it works pretty well, right? So it's kind of magic. But, that's why it's patented, and it makes a lot of money for whoever patented, right? So any questions about this? So this, again, I guess you guys have already turned in your project ideas, but there are definitely further ideas to pursue in terms of how, different images are coded up. The final thing I want to talk about today is another lossless coding algorithm that is mostly used in things like, it's used in things like fax transmission, but it's also used in JPEG, which we're going to talk about next time. And it's called run length encoding. And so the idea here is that there are some specific kinds of images that are very, very structured, right? So for example, if I have a fax of a page, right, it used to be that was just, I think it's probably still true that fax is binary, right? So I've got this image made up of black and white pixels, right? And so in some sense, what I expect is that, I've got this page where the top of the page is all, I guess, if we're using 0 for no ink and 1 for ink, there's like, lots of zeros, and eventually I get some ones that form, letters in the image. But for the most part, the image is made up of like big strings of zeros, okay? And so the idea is, well, why don't I just tell you, instead of coding every one of these zeros independently, why don't I just tell you how many zeros there are before the next one, right? And then I tell you how many ones there are until the next 0, right? So the idea is I'm telling you about the lengths of blocks of things instead of trying to encode every symbol independently. So the idea is very simple. And there are a couple of variations, but I can code the number of zeros between successive ones. Or, kind of an alternate, is that I can code the length of continuous black-white, I guess 0, 1 runs. Right? So to be concrete about this last one, so suppose I have like, this is my message, then I have some ink, then I have some other stuff like this. Right? So run length encoding would be, kind of the first way of doing it would be to say, okay, I say, okay, I've got 9 zeros followed by a 1, then there is no zeros between the next one, then I have 8 zeros before I see the 1 again, then I have a whole bunch of 1s together, then I have 6 zeros, then I have 4 zeros, and so on. The other way of doing it would be to say, okay, I have 9 zeros that are white, then I have 2 zeros that are black, then I have 8 zeros that are white, then I have 5 zeros that are black, then I have 6 zeros that are white, and so on, right? So I could do this either way. And in some sense, I'm not exactly 100% sure about how fax machines work, but depending on the type of document, one of these may be better than others, right? So if I have a document that is basically mostly like line art or a drawing on a piece of paper, then this first thing is going to be very efficient, right? On the other hand, if I have a document that's kind of like a graphic design that's got, big chunks of black blocks in the image, then the second one is going to be more efficient. And so maybe there's a switch inside the fax machine that says, okay, I'm either using method A or method B. I think typically run length encoding would be described as method A, where you're just coding the distances between the runs of things that you think are mostly going to be constant. And so then if I wanted to, on top of that, I could take these numbers and I could Huffman code them to get even better compression, right? So I could say, okay, now I think about these as occurrences of symbols. I think about how often these things occur, and then I do a Huffman code on top of that. Question? Yeah. So I mean, there are definitely, lots of layers of different levels of coding in all these kinds of real-world systems that are a little bit more complicated than what I'm telling you, but these are the basic building blocks. Okay, so then I could, Huffman code the run lengths if I wanted to. And so that's why for a fax machine, the compression is extremely good, right? So even if I start with a 2-level binary image, the compression for a fax machine is like 15-to-1 compression ratio. And that was an important thing, especially back in the day when the bandwidth of the telephone line was limited, right? So keep in mind that this, I don't want to date myself too much, but I think the fax machine was around before digital telephone lines, right? And so they needed a way to do basically analog transmission of images, and so there was an issue of bandwidth, right? So now, if you're talking about, behind your phone is digital, it's all fiber, they probably don't have the same kind of thing, but of course, they're still looking for ways to squeeze the most conversations, the most, the most parallel communication channels over all the fibers that they have. So I mean, even though things have gotten better, it's not like, you can just give bandwidth for free. Okay, so basically, that brings us to the end of the lossless stuff I wanted to talk about. And as I said, you'll find many lossless file formats online, especially like GIF and PNG and things like PDF files and zip files, right? Next time we're going to focus on lossy compression, which is something that's a little bit more unique for images, because in that case, we're going to design this lossy compression algorithm in a way that is going to remove information that is perceptually insignificant, right? And for that, we need to have something that has to do with, the human visual system. Okay, so any comments or questions? Okay, so on the homework, I'm going to ask you to basically